So, but most of the PhD scholars have returned to the campus.
Mhm.
UG, like the first year students, like they are all are doing online classes only.
Mhm.
Second year, third year, and fourth year, like whoever are willing, they are coming to the campus.
Okay.
Mhm. So now it is 2:30. So like we can start just a quick introduction about the today's workshop. So we are going to organize the workshop on recent trend in microwave and millimeter wave technology. And the speaker for our today's talk is Professor Kumar Vaibhav Srivastava from Electrical Engineering Department of IIT Jammu. Sorry, Electrical Engineering Department of IIT Kanpur. So we are going to organize this workshop under the umbrella of IEEE MTT-S Student Branch Chapter of IIT Jammu. So Student Branch Chapter of IIT Jammu, this IEEE MTT-S was formed in September 2019, and we are still in the process of getting the budgets for this year. So in this pandemic, we have organized several talk and webinar under the umbrella of IEEE MTT-S IIT Jammu. So we are with us Dr. Amit Kumar Singh, who is coordinating the webinars for this webinar under the IEEE MTT-S Student Branch Chapter of IIT Jammu. So he will tell us about MTT-S Student Branch Chapter, and then we will be going further for the today's event. So please, Dr. Amit.
Thank you, Saurabh sir. First of all, I would like to welcome Vaibhav sir for this webinar.
Thank you, Amit. Actually, because of your background, I could not recognize you. Yeah, sorry for that. Yeah, and
No
now I
problem,
just
no
saw.
problem.
Okay,
No
okay.
problem.
Sorry for that.
Yeah. Being part of MTT-S student branch chapter, IIT Jammu here, we formed this chapter in 2019, and followed by that, just last 7 to 8 months, we have conducted about 7 to 8 webinars by various eminent speakers in the field, including Gautam Chattopadhyay and Nashir Chahat from JPL, several Professor Emil from KTH Royal Sweden, and Professor Kang from Korea, and similar kind of professors and the speakers in the field. So now this year we started again with similar enthusiasm that the kind of work we should do for this MTT society and chapter. And we are very grateful and thankful to you, sir, for your kind talk and the kind of 4 continuous sessions and the lectures which you schedule. And here with us in this particular webinar, we have our students also, the participants from outside the campus also. So hopefully this particular talk is going to be too much useful for the beginners as well as the practitioners who is in the field from long time. And as our today's talk itself is on MIMO antennas, so probably it is going to be one of the interesting talk in the same session. So by this, I would like to welcome Vaibhav sir again for this particular talk. And now again over to Saurabh sir for just a kind introduction of Vaibhav sir to the speakers.
So, so just for about the today's, I will just mention about the speaker of today's talk. So, Professor Vaibhav Srivastava, he is currently associated with the Department of Electrical Engineering, IIT Kanpur, and he is serving as a professor there since November 2018. He has co-authored and authored more than 102 international journal articles, 2 international patents, and 142 conference articles in last 15 years. His extensive research interests are microwave antennas, metamaterial absorber, cloaking, FTDT technique, and MIMO antenna. So Dr. Srivastava received various national and best paper award, and he has served chairperson of IEEE UP section in 2018, and he has been serving as an executive committee member for the IEEE India Council since January 2019. So, um, so it is a pleasure for us to have Professor Srivastava as the speaker for today's talk, and for the today's the first session will be on the MIMO antenna. So just Sir Vaibhav sir is going to start his talk for the today's on MIMO antenna. So just Vaibhav sir, please.
Yeah, thank you. Thank you, Kushmanda, for inviting me. And thank you, Amit, for hosting this talk from the IEEE MTTS student branch chapter. Uh, so, and I am also thankful to that IIT Jammu for actually giving me this opportunity to present my work. So some of the work which I will be presenting that is also contributed by Kushmanda. So,
Yes.
so
Thank you, sir.
yeah. So can I share my screen now, Kushmanda? Yeah, now
Yes,
it
yes,
is
sir.
working. Yeah,
You can
yeah,
please.
yeah, it is working. Yeah. So the way actually I have oriented this today's talk, so I will be actually giving that the some introduction about the 5G and how this MIMO antenna can fit into 5G. Then I will actually cover some of the basic about the MIMO antenna, and then some of the structure which we have designed, fabricated, and measured at IIT Kanpur. So initial part, we will be actually covering about the basic of MIMO antenna, and the second part we will discuss about the some design aspect of MIMO. So if we will go with this wireless traffic, so if you'll find like currently the way this data and especially like the because of this COVID-19, you have seen that the this data requirement has actually increased enormously in like the last 5-7 months. So the way if you'll see that this is from that the Cisco website I have actually taken. So the way the data traffic per month it is actually increasing. This is like the from the 7 exabyte which was in 2016 until 2021 it could be like the 49 exabyte per month data traffic. And whenever we are actually talking about this exabyte, so this is like the 1000 petabyte, it is 10 to the power 6 terabyte or 10 to the power 9 gigabyte. So every month we are having that the close to uh, very high data traffic, which is like the some 50 exabyte of the data traffic we are seeing. And all those things is actually happening. So there should be there some contribution. So like currently we are in that the 4G and then we are actually moving to the 5G. So the reason actually we are going from the one generation to other generation, we are looking how we can get more data speed. So there are some of the some data analogy like so so currently like the 20% of the total IP internet protocol traffic that will be through that the mobile handset. So it means like the instead of like people now preferring to use that this internet connectivity on the desktop based system, people are actually moving on the mobile system. It could be like your laptop, or it could be like your tab, or it could be that any handset. So mobile data traffic is keep on increasing. And if you see the number of device also per person, that is also it is increasing. Like the each person has at least like the one mobile, one tab, and one laptop. Many people are having like the smart watch, or they are having some more gadgets which are actually connected through internet. So over the time we are actually using more and more devices, and they all are connected on internet. It means like I need that the more data speed. So in 4G, like generally like the 4G claim like it is like 100 Mbps, but the average speed you get sometime like the 6.8 Mbps. So the mobile network connection speed will increase itself from 6.8 Mbps to the 20 Mbps by 2021. So average speed, though like the 5G it claims like the 1 Gbps, but like actual speed what you will be getting that will be close to the 20 Mbps. And the 4G currently, like by this 2021, 58% of the data traffic that will be handled by 4G, and the rest either it will be like the 3G or 3.5G, or some of the country are actually going into the 5G traffic. So if I will go from the 2G to the 5G, if I will compare to 4G, so my mobile data traffic that is increasing actually like the 1,000 times. My device which are actually connected on the network as compared to 4G, that will be like the somewhere in the 10x to the 100x. So it will be like the 100 times more device will be connected on the 5G network as compared to 4G. Then we are also expecting like our latency rate also will be reduced by the 5x times. and the in-to-in data transfer, that will also increase like so currently like the earlier, like we are having like the more thing which are actually lying on the internet and we are just downloading it, is like the single way traffic. But now the in-to-in, like we are actually preferring to have the mobile, we are having video call with the some person, or we are actually having the continuous connection between the end-to-end user. So that will also enhance in the 5G. And then also we are hoping that we have to reduce my battery life. That will be like 10x times, the battery life will also increase. So these are like the basic thing which we are actually talking in 5G communication system. So currently like this 5G, that is like going from like some of the country has also already started the deploying, mostly like the South Korea and some part of the US and Canada. They are actually looking for the deployment of 5G. Some people are like that the India is still like the looking and looking to have the commercialization, and most people like the toward the 2022 in we will have the some commercial 5G network in India. So if you go with the 5G band, so they are like the earlier it was proposed like close to like the 30 gigahertz people have proposed over there, but it looks like the most of the 5G will go to the sub 6 gigahertz, and most of the now network which people actually talk about 5G is like the 3.4 gigahertz to the 4.3 gigahertz. In that frequency range, people are targeting this 5G network. And there is like the one is also like if you go with the GSM, which is like the 900 megahertz, 700 to 900 megahertz, that also like the people are looking for one of the application in 5G. So advantage is like if I go from the sub 1 gigahertz to sub 6 gigahertz, definitely like my frequency is actually increased. And from here to if I will go to the millimeter wave, again that the frequency is increased, so my data speed will be actually more. But the thing is like the technology at 28 gigahertz is still not matured, and the propagation model is now not well understood at 28 gigahertz. So the 5G network is now that's why it is planned at the sub 6 gigahertz, where your channel model is already well defined, and you are having the larger coverage rate like as compared to like the network coverage. So network coverage is more in sub 6 gigahertz, because the moment you are actually going on the high frequency, your coverage range will be actually reducing. So people have to come up with some model where actually like the really that this millimeter wave can be used. So this is like the quick glance for the 1G to the 5G. Like 1G, we are having this speed. This was like this telephony, and at that time we are getting the speed of the 2.4 kilobits per second. If you go from the 1G to the 2G, this was like the 64 kilobits per second. And at that time, like the SMS facility was actually started over there. And then actually like if you'll go with the 3G, so then we are actually having this internet connection. And at that time we were getting something like the 128 kilobits data. And then the 3.5G, then we have actually coming the data speed of like the 2 Mbps. 4G, like the ideal speed, they say like they should be the 100 Mbps. And the 5G, people are actually targeting for 1 Gbps of the speed. So but it's still like earlier like it is like the theoretically it is launched by the 2019, but it's still like the commercialization is yet to be done. So if I go from here 3 to 4G and 4 to 5G, so 4G that the people were actually talking about that the MIMO antenna system, and the 5G people are actually talking about that the massive MIMO system. Okay, so MIMO is like the multiple input, multiple output antenna system. So this is like the one of the way how you can increase your data speed. So it is like the multiple antenna which will be operating simultaneously for transmitting and receiving. So that is like the MIMO antenna system. So 5G says that the instead of like the let's say that the 4 element or 8 element, you are talking about like the array of the element. You are talking about like the some 64 element or 256 antenna element on one side of either on the transmitter or the receiver side. So that will be like the massive MIMO system. This one will skip that part. So the way actually higher data speed can be expected. So one of the method is like you use the multi input, multi output system. So that is MIMO system. Then people are also talking about that the adaptive beamforming, which I will be giving some glance on the adaptive beamforming. Then other part is like this signal processing or communication part. Actually, it goes that you use that the AMC coding scheme, or you use that the multiple access. So my talk for today, it will be actually concentrated on the use of multiple input and multiple output. So what basically it does, so if you are having the data in where actually like your data is going from the here. So first thing is that I am converting data serial stream of the data to the parallel stream. So it will be like the serial to parallel converter. So this is like my data which is actually coming to system. Then I'm actually converting the serial to the parallel bit. Then this data stream that will be actually passes through the encoder. Then it go to the modulation, and then it goes to the antenna. So this is like the one antenna over here, and similarly like I will have the more number of antenna which will actually sitting on the transmitter side. Similarly, I will be having the antenna sitting on the receiver side. So this is actually transmitting, and then I'm actually receiving with all those receiver antenna. Then I do that some signal processing, then demodulate, decode, and then I'm actually doing parallel to serial converter, and data is actually out. So in this way, like in the MIMO system, people are looking to increase the data speed. So instead of the transmitting the signal on single antenna and the receiving the signal from the single receiver antenna, people are actually transmitting data in the parallel stream. So it is like from the serial to the parallel data stream. Actually, I'm transmitting over here. But it is not simple as the way it looks like. If I say that it is like the wired connection, and if you are transmitting the data from the one into other end, then it is very easy, because like the one of the transmitter will only talking with the one of the receiver. It is like let's say if I say that this is like a T1, T2, T3 to the Tn, and here this is like R1, R2, R3 to the Rn. So it means like the T1 will be talking with the T2. T1 is also talking with the R2, because this is like the wave which you launch from the antenna, and then it is propagating in a space. And once it is receiving, so it is not only received by this antenna, it will also be received by the various stream. And that's why that you need that some signal processing method, so that you can actually separate out, and then you can join that all the signal. So that's why like for the antenna designer, it is not that easy to design that the complete thing. And that's why that you need that the better channel modeling for this one, which actually the communication people are doing. uh, so whenever actually we say that the MIMO antenna system, so the thing is like, let's say if I'm operating the CISO is like the single input, single output. If I'm going from CISO to the MIMO, so given that the bandwidth, if I can actually transmit the more number of data bit, then only I will say that my channel capacity has actually enhanced. And then actually I'm saying that my overall the data transmission has increased. So this is like some of the MIMO system you have already seen, like you have seen that like this is like Wi-Fi router which is having the 3 element. Sometimes you have seen that the 4 element, and sometimes you also get that this type of router where actually patch antenna is sitting. So those network people. So these are like the MIMO system. This is like the normal. It is 4 element or the 8 element system. This is some of the our work which we will discuss later. So what actually in the MIC MIMO people are talking about? So MIC MIMO, it will be like you are having this base station. So currently, if you have seen that the conventional base station, so it is actually having that the 3 sector or the 4 sector. I mean, like if you talk about the 3 sector, it is like the 120-degree sector, and within the 120-degree sector, you are actually having that the one fat beam which will be transmitting, and all the user present in that region, they will be actually receiving the data. So it is like but in the MIMO system, it will not be like the one sector is actually having one antenna, or I can say that the some 4 element or some 8 element, because they need sometimes the electrical tilting also. So but that antenna is having like the one beam. But now people are actually talking about the MIC MIMO, where the tower will have the more number of antenna. It could be like the some 256 element, and then this main base station will be actually transmitting data to the sub base station. So like the user of this building, they need not to directly talk to the main base station. They will be actually talking to the this sub base station, and where I can have that the one dedicated beam which will be continuously connected to this user. Okay, the user which are this sub base station. Similarly, I can have that the one dedicated beam which will be connected to this building or this building or this building, and then the people who are actually lying within that the in this building or the close by this building, they will be actually communicating to this sub base station. So in that way, I can have some dedicated beam to that the main I will say that this main user, and then from this one they are actually going to the sub user. It could be like the circular area of the antenna, it could be linear area of the antenna, it could be like the rectangular area. It depends upon the how you design those antenna. People are also targeting like the you can have the dedicated. So this is like the 120-degree sector one once actually it is shown here. So let's say if I have the 4 user which are actually lying, so instead of the single fired beam, I'm actually can have the dedicated beam towards this user or dedicated beam towards the particular user. The advantage will be like if I have the dedicated beam toward the particular user, I can actually have that the connection for the more time. Otherwise, currently what happened that it is like the either the TDM or the FDM, and it will be actually connected for the very less time. But if you are having like the very adaptive beamforming, you can actually connect over there because they are having the more number of antenna which is present on this base station surface. So individual user can have that the some dedicated beam for longer duration, and then again you can actually apply the TDM, FDM, all those technology. It also says like that if I will go with the massive MIMO, so instead of the scanning, so this was like the conventional one fired beam, but if I will have the massive MIMO over there, I can actually have beam forming in the vertical plane as well as I can have the beam forming in the horizontal plane. So beam forming in the vertical or beam forming in the horizontal plane will give the advantage that I can have the dedicated beam toward the user. So let's say if this is my antenna, so it is actually connected. Let's say this is like the one high-rise building. So I can have user which are actually connected with the individual beam, and from this base station I am launching the EM signal, and which is received by this particular user, and each user like on this floor you can say have the dedicated beam. Similarly on the ground I can have the dedicated beam toward the individual user. So those could only be possible if your base station have that the more number of antenna, or I will say that the massive number of antenna. So this is all about like that the some thing like the why we are actually looking for the MIMO antenna, and then we will go with the some basics like the how the MIMO antenna can increase your speed. So if you go with the very standard that the Shannon-Hartley theorem and try to find out what is my channel capacity. So channel capacity that is given by B log to 1 plus S by N. B is my bandwidth and S by N is like the my signal to noise ratio. So C is channel capacity, B is bandwidth, S is that the average received signal power, N is that the noise average noise power, and S by N is that the signal to noise ratio. So if I know this one, I can actually calculate that what is my channel capacity. So this is one example. I will try to make you understand like why that this from the CISO channel, if I go to the MIMO, what will be advantage. So if it is like the single input, single output, and I'm actually looking the SNR of 20 dB and I have the bandwidth of 4 kilohertz. So what will be my channel capacity? So signal to noise ratio, that is like if I 20 dB, if I convert in the linear scale, that is 100, and bandwidth that is given to the 4 kilohertz, it will be like 4 log to 1 plus 100. And if you try to solve, I'm actually getting that the C prime, which will be like 26.63 kilobits per second. If I will actually go, let's say if I will go other way around, I want to transmit that the data with the 50 kilobits per second and I have been given the bandwidth of 10 kilohertz. So what will be the signal to noise ratio? You can actually calculate like 5,000, and this is like 10 kilowatt. I can calculate the signal to noise ratio, which comes there I should have 14.9 or 15 dB of the signal to noise ratio. So this example actually is showing like the CISO channel, which is like the single input and the single output. So I have the one transmitter here and I have the one receiver here, and my channel response that is governed by the h, t, comma tau. So h is my channel response, t is like the with the as a function of time, and tau is like your delay factor. So if I assume that my channel, this is like the time and the frequency invariant, I can actually find out like the h, t, comma tau. It is time and frequency invariant, so it will be like the h. So y will be like hx plus n. So y is like the whatever the signal I am receiving. H is that the channel response. X is that the signal which is transmitted by this transmitter, and n is that the noise introduced by this channel. So y equal to hx plus n. This is like my signal. So it said the y is the received signal, s is transmitted signal, and n is that the additive wide Gaussian noise. So it's the CISO. So now actually I am defining this one, which is channel capacity, which is that the kilo, which is bits per second and per hertz. So because the bandwidth is always available, so I am looking at the within that the given bandwidth, what is the response of the CISO channel and what is the response of the MIMO system. So I'm normalizing respect to the this bandwidth. So your unit of the C is now the bits per second per hertz. Okay, so this bandwidth part is now not coming. So CISO, that will be log to 1 plus PT over sigma n square. PT is like the power transmitted by this transmitter, and the sigma n square is the my noise power, and H is like the my channel response, and this is like the H square. So PT multiplied with the H mod square, that will be like the whatever the signal is received over here, and the sigma n square, that will be like the my noise power. So log to 1 plus PT over sigma n H square, that will be my CISO channel capacity. Now in this one, in the CISO channel, if you look like this is the 1 plus PT over sigma n H square, I assume that my signal to noise ratio, that is very high as compared to noise. So what will happen, this number that will be like the pretty high as compared to 1. So I can actually neglect that this 1. So what will be like C becomes like the log 2 PT over sigma n square mod H square. So if I will actually expand this one, this will become the 2 log 2 H and plus log 2 SNR. And now the C, which is like the kilobits per second per hertz. Now here, if I say that you have to enhance your channel capacity, so there is two options. Either you work with this H, which is that your channel response, or you work with the SNR. So if you are working with the SNR, if you are making that your SNR to be the double, then your channel capacity, that will be only increased by 1 bit. Okay. So if your SNR is double, or the SNR is like if I will increase to the 3 dB, then my channel capacity will be only increased by 1 bit. So it means like, here it says that in the high SNR, a 3 our energy on increasing this one, we have to work on this H, which is like my channel response, which is like the log 2 H. So if I'll go with the MIMO channel, so this channel, instead of the H, this H will convert to the matrix form. That is now I'm saying writing the channel matrix. So MT, that is like the number of transmitter antenna. MR, this is like the number of my receiver antenna. So this Y, so Y instead of like some single number, it will be like some vector. and that will be governed by the hx plus n. And y is like the received signal vector, x this is the transmitted signal vector, n is that the added white Gaussian noise vector, and h is my channel matrix. So this h will be giving me that the h11. H11 is like the how my transmitter 1 is connected with the receiver 1. So this is like h11. H12 is like the how my receiver 1 is connected with the transmitter 2. Using, so it will be the empty cross. So empty is number of row and then the one column. This is like the column vector. This is again the column vector, and h the dimension will be the mr cross empty. So if I am using more number of transmitter and receiver, the advantage is that I am changing my channel matrix. So this y, which is like hx plus n. So this was like the my CISO channel capacity. If I will actually go with the MIMO channel capacity, so this instead of this single number, it will convert to the matrix. So this C MIMO, that will be log 2 base determinants of this I, which is identity matrix, plus PT over MT. So PT over MT is like PT is like total transmitted power, and then I'm dividing to empty number of antenna on the transmitter side. So that will be like the my signal power, and divided by this sigma n square, which is like the my noise power, and this PT by MT is multiplied with the your channel response, which is h times that h Hermitian. So this will be giving me that what is the power received at this receiver antenna. So this is all those things you can actually do. So this channel capacity, that will be modified this expression as compared to this CISO channel. So it says like that if you are having this channel which is independent and identically distributed. So if this matrix, which will be defined for the independent and identically distributed complex Gaussian variable, that will be governed by this channel response, then what will happen? You can actually do that the mathematics, and you will find that this C MIMO, that will be m times CISO. So C CISO is the channel capacity of the CISO channel, and C MIMO is the channel capacity of MIMO channel, and that will be, so C MIMO will be m times CISO. So it is like the m, this m is the minimum of MR comma MT. So MR is number of receiver antenna and MT is number of transmitter antenna. So what it says, if you are having independent and identically distributed this channel matrix, in that case, the channel capacity as compared to CISO channel will be improved by m times, and this m should be the smaller, like minimum of the MR or MT. So so just for the quick example, let's say that if you are having the 4 transmitter and the 4 receiver, then and this channel is actually independent and identically distributed, which is IID. In that case, your channel capacity will be enhanced to the 4 times. So if you're using 4 transmitter, 4 receiver, it doesn't mean that the channel capacity is actually increased by 16 times. It will be increased by 4 times. If you are having 4 transmitter and the 1 receiver antenna, then there is no enhancement in the channel capacity. If it is like the 4 and on the receiver side, it is the 2 antenna, so channel capacity will be enhanced by the 2 times. So it says that under the ideal condition, it will be almost like the transferring the data in the parallel operation instead of the serial operation. So that is like the ideal condition of MIMO channel. So this is like a thing. So here actually it gives like some examples. So here on the x-axis, it is plotted on the number of antenna, and on the y-axis, it is actually transmitted it is plotted the bandwidth. So it says that let's say if I want to get the channel capacity of 1 gigabits, so if I'm using single antenna, So I need that the 150 megahertz of the bandwidth. But if I will go actually like the 6 antenna system, like the M, like the it is like the M cross M MIMO antenna. So if I'm using that the 6 MIMO antenna, I will be required, because now that the is actually your uh, total like channel capacity that will be increased by 6 times. So your the bandwidth requirement will be actually like the lesser. So it is like here it was the 150 megahertz bandwidth was required for single antenna, and for MIMO system you for the same channel capacity for let's say that the 1 gigabit per second, I need only the 30 megahertz of bandwidth, because of the sixth number of antenna your channel capacity is increased by 6 times. So this is the one way. So this is like IID, which is like the independent and the identically distributed system. And this is like the, if you are having the correlated system, so maybe you require that the more bandwidth. Okay. Yes, it is same thing. Another thing, it is actually like this plot. So this side, it is like the number of transmitter and receiver, and this is like the how many bits per second per hertz I'm actually getting. And this will give you that with the different SNR ratio. So it says like that if your SNR ratio is that small, even the improvement in the number of antenna will not be actually significant. But if you are having, let's say, SNR of 20 dB or SNR of 30 dB, even that the one more increment in the antenna, there will be large improvement in your channel capacity. So this is like the when the SNR is 10, this is SNR is actually 20, this is SNR is like the 30. So if SNR is like 30, so for 6 number of antenna, I can actually get 50 bits per second per hertz. If like it is like 20, then I will be getting something like the 35 bits per second per hertz. So if you are increasing that the SNR, and the same time you will also increase the your number of antenna, the enhancement in the channel capacity will be significant. So in like CISO channel, we actually line of sight communication is actually better. Otherwise, like the once the signal reaches to the receiver, you will be having that the fading. But in MIMO system, non-light of sight communication is like the helpful. And the people have actually shown that if you are having the non-light of sight communication, then the channel capacity is actually more. So you are actually trying to create this H, which is like a channel matrix. You want the, if line of sight communication matrix will be, line of sight communication will be there, then your H matrix will be the sparse matrix. But if it is like the multiple paths are actually coming into picture, then the each path will actually contribute to the what is your channel response. So the channel response matrix will have that the well distributed. So that's why like the non-light of sight communication will be better for the MIMO antenna system. Okay, so till now, like whatever the work they are doing, these are mostly done by like the communication people. The problem start for the RF people is like if I am having the more number of antenna which are sitting on the same side of the, let's say either on the transmitter side or the more number of antenna is actually present on the receiver side. So we are only talking about how the T1 antenna is actually communicating with the R1 or how T2 is communicating with the R2. But what about that the communication is happening between the T1 to T2 or T1 to T3 or T1 to T4, or similarly on the receiver side, which is that R1 to R2 or R1 to R3 or R1 to the Rn. So those things we have to actually uh, talk about, and then that actually decided how that your MIMO antenna system has to be designed. So if those things are actually designed, so this H matrix, which was only talking about the this channel response. So in channel response, there will be like the two additional matrix will be coming. One is that the RR, which is talking about that the how the antenna present on the receiver side, how they are actually connected, and RT is like the antenna which are present on the receiver side, how they are actually connected over there. So those thing will also come into picture. This HK, so this H will be modified as the HK, which will be R 1 by 2 HDR 1 by 2, and this will be like the transpose. So before going to this one, like so this will actually affect the my channel capacity. I will come to this one. So once actually we are designing this MIMO antenna, so some of the parameter which will be required in addition to that my fundamental antenna parameter. So for the fundamental antenna parameter, we actually looked at what is my reflection coefficient, what is my input impedance profile, what is the 3D or the 2D radiation pattern, what is the directivity and gain of the antenna, what is radiation efficiency, and what is axial ratio. So these are like the when I have the single transmitting antenna, we talk about this parameter. But if I'll go with the MIMO antenna system, along with this parameter, we also need to talk about some additional parameter which are called ECC, which is the envelope correlation coefficient, ECC, which is rho e. We need to talk about the channel capacity loss, which is CCL, total active reflection coefficient, which is TRC, and mean effective gain, which is the MEG, which is mean effective gain. Uh, so we will actually try to understand one by one what are those parameters. So let's say like I am having the antenna and they are actually transmitting. So now I am talking about the antenna which are present on the same side. It could be either transmitter or it could be either receiver. So the correlation coefficient is actually governed by the E theta. So E theta is like your theta component of the field, and I stand for the ith antenna and J stand for the jth antenna. So I am looking the how the field radiated by the first antenna is correlated with the field radiated by the second antenna. So E theta, sorry, E theta I, which is uh, the theta component of field for the ith antenna, and how the theta component of the field with the jth antenna, they are actually correlated. And similarly, the theta I, phi I, so this is like the phi component of the ith antenna is correlated with the phi j, be like the phi component of the jth antenna. So I'm actually taking the product of these two, and I'm taking the product of these two. So E theta of the ith with E theta of the jth antenna and E phi of the ith antenna, how it is correlated with the E phi of the jth antenna. Then I'm actually integrating over the d omega, and omega is like the function of theta and phi. And then I'm taking the square root of E theta I and E theta I and E phi I. So it is the total field, radiated field of the ith ith antenna, and this one is the total field of the jth antenna. So I'm actually looking at these two number, E theta I, theta j, and E phi I and E phi j. So this will be like the total integration limit, and then I'm dividing with the square root. So the envelope correlation coefficient is that the mod of this square, and that will be actually governed by this expression. So this will be giving the how. So what actually I want so I said like we want like all those antenna, they should not be correlated. If they are correlated, their channel matrix, they will also be that correlated. So you won't be getting the identical and the independently distributed matrix. So in that case, I want that there should not be that a strong correlation between the ones actually I am transmitting from the one set of the antenna. So you have to actually do this calculation. Then it also depend upon the, let's say in the some side, even though those two antenna are correlated, but whether the power spectrum are like let's say I'm transmitting the antenna and that it is received by the receiver antenna, but let's say in some direction they are correlated, but there's no power available in that direction, so that the correlation will not be the significant. So it says like along with the field of the antenna, which is E theta I and E theta j, we have to also see that what is like the power available in the theta and the phi direction from where actually the power is actually coming. So it says like this will also depend upon what is the propagation scenario. So the modified expression will be zeta, which is like the average power available in the theta, as well as what is the ratio of the average, what is the power available in the theta component and what is the power available in the phi component. So it will be like the chi divided by 1 plus chi e theta j, and plus 1 over chi e phi I e phi j p phi omega. So p theta is like the power available with the theta component, p phi is like the power available with the phi component. And then those terms, that the electric field of the individual antenna, that can be actually represented with the term, this is GEI and GEJ. So GE denotes that the mean effective gain. So this is like the one of the thing you have to actually calculate if you are defining your MIMO antenna system. And sometimes like to define this electric field, like the calculating the this correlation coefficient from the electric field, people also try to correlate this thing using that the S parameter. But sometimes people have found out that this method is not very accurate, and this calculation of the field is more accurate. But in this one, like what you are supposed to look, like first thing is that your electric field is function of frequency. So over the frequency spectrum, you are actually trying to calculate the correlation coefficient. Then you are having the two component of the field. One is the E theta and E phi. And let's say if you are having the m number of antennas, so it is like the m number of variable. And then you are actually integrating this thing over the d omega. So d omega, which is function of the theta and phi. So for each theta and phi, you are trying to integrate. So you need that the very large memory to compute this one, as well as that the you need that the good computation facility to calculate this correlation coefficient. So sometimes people have actually from this one, they try to derive S11. The difference is like the S11, S22, and all those one are the port information. Okay, whereas the field is actually covering that how the current is distributed all over that the antenna. Okay, so there is not like that the always that the accurate mapping from the electric field to the S parameter. So this one is not very accurate. But if you are actually going for the fast computation, S parameter is only like the function of frequency. So you are having the 4 variable, and you are having uh, the each variable is only function of frequency. So here like the calculation is that the very fast, but here it is like the computationally inefficient, but it is very accurate. So generally, as per the standard like ECC, that should be like the less than 0.5. Then if you are designing any antenna, if the ECC is less than 0.5, the antenna is actually good. But generally for the antenna designer point of view, you work for the ECC that is less than the 0.1. Then other one is like this channel capacity loss. So I said that if you are having this RR, which is like the giving the matrix, like how the antenna on the receiver side, they are correlated, and RT is like the how the antenna sitting on this side are correlated. So C MIMO, which is like the MIMO channel capacity, that will be modified with C MIMO ideal. C MIMO ideal is like these matrices are not present over there. There is no correlation that are actually present. So this is C MIMO minus C loss at the transmitter side on this side, and the C loss on the receiver side. That will be actually like this antenna. So your channel capacity, that will be modified as the C MIMO ideal, that will be log 2 rho m over m HW and HWH. So HW is stand for this one. This rho is like the whatever is like your total power transmitted and divided by the m. C loss T, that is minus log 2 base this RT expression, and this C loss R, that is minus log 2 RR. And this one can be correlated with your S matrix. So that will come that the minus log 2 I S T Hermitian and ST, and this is minus log 2 I minus SR H and SR. So it is actually showing like how this set of the antenna are correlated, and how this set of the antenna are correlated among themselves. And if those will be there, then you will have the lesser channel capacity. So it says that the CCL is generally predicted that for the antenna designer should be less than 0.5 beta bits per second per hertz for the 4G wireless communication system. There is one more important term that is called like the total active reflection coefficient. So now you are not only having one antenna, you are having the multiple antenna. So what is that the total power which you are transmitting? So it should not be like that my T1 is transmitting and the T2 is actually receiving. Okay, our T1 is transmitting, T3 is actually receiving. So it means like my antenna is really radiating. So I have to actually see that what is the total. So this is like sigma I equal to 1 to m bi square. So I square is corresponding to that what is like the power that is radiated by like which is coming out from the antenna port, and the AI which is actually like the AI is like the voltage incident to the antenna port, and AI square if I'm taking, so it is corresponding to the my power. So this is like the summation of the all the power which is uh, incident on the antenna port, and this is like the power that is coming out from the antenna. So it says like the if I want to, so earlier like my active reflection coefficient, how we actually calculate active reflection coefficient is like what is power coming. So B1, let's say if it is the CISO system, so B1 is like my reflected and A1 is my incident. Now I have the multiple antenna system. So I will actually launch the power on all the antenna port, and then I will see that how much power is coming back to antenna port. So that is like the way if I will calculate like all the power or all the voltage reflection coefficient which is coming out. So B1 square plus B2 square plus B3 square to Bn square, and divided by the square root of A1 square, A2 square, A3 square. So A1, A2, A3 are like the incident voltage, and B1, B2, B3 are the my reflected voltage. So if it is like the two port system, it will be actually like gamma AT, that will be B1 square plus B2 square over A1 square plus A2. And the B1, if it is two port system, that can be written as like a S11 A1 plus S12 A1 mod square, and S21 A1 plus S22 A2 mod square. Now here it will also depend upon like the what is the individual I'm putting the voltage. So what is like the amplitude? Along with the amplitude, it is also like the what is the phase of individual port. So let's say if it is they are all excited with the uniform amplitude, but their phase is also going to play that role. So whenever you are actually designing the MIMO antenna system, you actually vary that this phase, this theta I from 0 to 180 degree, and just see that the under what case your total active reflection coefficient, as for the good design, that the total active reflection coefficient that should not go above to that the minus 10 dB. It means then only that you are radiating that the 90% of your power. So this is like the some design that we'll be actually talking in the next session. So I will actually end that the first session here. So if you have the question, we can actually take.
So I request all the audience, like if there is any questions, so they can ask.
Hello.
Yeah.
Uh, Sir, in the 120-degree radiation pattern, you told that there will be one means dedicated beam forming for each and every subscriber. So how to handle if the subscriber density will be more? Means what will the
Then
limitation
actually
over the channel?
no. So then actually you will go for the TDM and FDM. All those things will still be there. But what actually point was like if you are having let's say in this picture, if I have the more number of antennas, so currently like I am within this 120-degree sector, there is like the one fat beam which will cover the all the subscriber. Now with the one fat beam, I'm trying to cover. Instead, I'm actually having dedicated beam. So one antenna is actually transmitting, like one set of the antenna is transmitting, and this is received by the one user. Another set is transmitting, which is received by the another user. This is transmitting. This user is connected. So I'm not saying that this beam will be only talking with this user continuously. So after some time instant, then this will be actually connected to the other user that is present on the system.
Okay, sir. Okay.
Okay.
Sir, is there any limitation on the number of arrays that you are using on this 120-degree pattern? Like you told that previously that 264 or some 256 something.
So currently, like it depend upon the how thin you are actually looking at your beam. So if you are looking at a very thin beam, it means that the more number of element you have to use. And if you are looking at the thick beam, that even with the lesser number of element, you can actually cover those user. So it depend upon the what is like how many users are there and what is like the availability of space that is present on the tower. So all those things will become important.
But at the same time, the power constraint will be there, right? If we increase the number of antenna array, then the transmitted power will require more in that case.
No, not necessary. If you are using the more number of antenna, then you will be actually getting the very narrow beam width. So then you can actually go for the longer distance. Okay, so more number of antenna, then your gain enhances, and if the gain enhances, that the transmitted power can be actually reduced. So they are not like the one-to-one mapping.
Okay, sir. Okay.
Yeah.
Oh,
Thank you, sir.
what is the use of TARC? TARC?
Yeah, TARC is actually the objective is like if you are having multiple antenna which are actually present on your system. So what you look, it should not be the case like the I will only see that what is my S11, S22, S33, all those only as per like these parameters. We have to also look the if my antenna 1 is transmitting, let's say my T1 is transmitting, it should not be the case that it is received by the T2 antenna. T2 is because T2 is also supposed to transmit the signal. So if you design the network, this MIMO system where the T1 is transmitting and it is received by the T2, it means like the power is going from the one of the port and it is coming to the other port. So only looking the S11, S22 to SNN, that may not be enough. So then you have to use the total active reflection coefficient such that you can see that really the system is transmitting the enough power or not.
Since this is a very big computation for large arrays, then.
Yes, yeah, it will be big composition for a large array.
Yeah. Thank you.
Yep. Any other question?
No, sir.
Okay.
So if there is no question, then we can like after 30 minutes we
we can
with the
start
next
at
session.
4. Yes, yeah,
Yes, we can start with 4 for the next session on
Okay.
MIMO antenna.
Okay.
Okay.
Kushmanda, if I'm delayed by 5 minutes, will it be fine?
Yes. No issue, sir. No
I will
issue.
try to come
So,
back by.
so it is the same link and we have made the setting like any users can join at any time. So there is
Okay,
no issue
okay.
in that.
So I may get delayed by the 5 minutes because I have to go to the DOSA office to sign some paper and then I will back. Huh?
Okay, sir.
Okay. Thank you, Kushmanda.
Welcome, sir.
Thank you, Amit.
Yes, sir.
Thank you, sir.
So Kushmanda, I'm
Yes, sir.
back, so we can start at 4. Huh?
Yes, 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 sir. Yep. Sir, I think we can start. It's now 4.
Okay.
Okay, sir.
Should I start, Pushpanda?
Yes.
Okay. So first part of the lecture, we have seen like what are the so why we require that the MIMO antenna, how it will help to increase my channel capacity, and what are like the main parameter for which the antenna designer should concentrate if they are working on MIMO antenna. So the parameter are like the ECC, parameter like the torque, mean effective gain, or channel capacity loss. So those are the additional parameter people calculate if they are designing the MIMO antenna. So here I will be discussing like the some 4-element MIMO antenna, which is basically designed like by our group. So this is like the first one. So it says like this one is quad band. So quad band means like it is like the 4 band, which is like so this is like currently it is the picture which is shown is like the single element, and this single element itself is quad band. So the way this antenna element look like, I am having this CPW environment. So this is my main line and this is CPW line, and then this CPW line is actually extended over here. So that will behave like monopole, and then within the monopole we have created this interdistal capacitor, and this monopole is loaded by this SRR, which is split ring resonator. So by loading the interdistal capacitor and by loading the SRR, this antenna element can behave as a quad band element. So if I will go with the design of this element, so this is like the, if you are having only this monopole antenna, you are getting the one resonance, that is like the, it says the case 1, you are having this resonance that is coming around the 2.6 gigahertz. And if I keep on actually loading, so if I, let's say that if I'm loading the SRR, which is case 2, because of SRR, you are actually getting that this band. Then if I have the interdistal capacitor only, so then also I'm getting that there are 2 band. One is blue line, which is actually like shown over here. Then I'm actually having that the 2 additional. So this one interdistal capacitor are actually creating that the 2 resonance in this monopole. And if I will take the full geometry where the interdistal capacitor and SRR are actually loaded, so this will behave like quad band element. So now this quad band element, if I will orient in the orthogonal way, so this is like the orthogonal way we are actually orienting. So in that way, we can actually get 4-element MIMO antenna, and which will operate in 4 bands. So this is like individual band. So this is like the 1, 2, 3, and 4 band. It is actually shown, and the orthogonal placement actually will give you actually advantage, like as compared, if I compare to the one and antenna element 1 and antenna element 2, they are placed in orthogonally. So it's means like that if I will be looking the field in the far field, so let's say if this antenna is actually providing that the E theta field in the far field direction, this will actually provide the E phi in the far field direction. So they will actually provide that the polarization diversity. Okay, and this element and this element, they are actually like the way the feeding is like the 180-degree, and other one is also like that they have the space diversity. So the antenna element is kept, one is actually kept over here and 3 is actually kept over there. So they are having the space diversity. So whenever you are actually designing the MIMO antenna, so you should actually avoid the you should have the very less correlation. To have the very less correlation, you should have the space diversity among the element, or you should have pattern diversity, or you are having the polarization diversity. So these are like the three way you can actually design the very good MIMO antenna system. So this one is especially like orthogonal placement, and you can see like these are like the various resonance which are actually shown, and these are like they are S21, S31 or S41. Like if I'm feeding the antenna element 1, so this one is like the S11 curve, and these are like how the power is reaching to antenna 2, power is reaching to antenna 3, or power is reaching to antenna 4. So they are actually like the below minus 20 dB. So the isolation among the element are actually good. So this is like the fabricated element. This is like your copper on the front side. This is like your CPW excitation, and this is interdistal capacitor, and SRR are placed over here. And these are like the measured response. So measured response also you will find like the 4 band, and the S1, S21, S31, and S41. They are actually the transmission coefficient are below or close to that 20 dB. Then I said if you are designing the antenna element, you should have the this correlation coefficient. So this is 1, 2 stand for the how my antenna element 1 and 2 are correlated. 1, 3 is like the how antenna 1 and 3 are correlated, and 1, 4 is like the how antenna 1 and 4 are correlated. So as per the design thing, your antenna should actually provide the envelope correlation coefficient less than the 0.05. So if you see that for all those one, this antenna coefficient, this correlation coefficient is like the below 0.01 in all that band. These are like your operating band. So it means like you are having very good correlation. So this is like the from the field we have calculated, and this one is like from the S parameter we have measured that this correlation coefficient rho E12, rho E13, and rho E14. So this is one way to actually have a good correlation. So in this one, like if the previous case, we have found like there is no pattern diversity, but this is the element where actually we are having the pattern diversity, as well as I'm also having the common ground. So common ground is like all the 4 elements will be actually using the same ground plane. Otherwise, the earlier case, they were isolated ground. So each are not actually. So let's say that if you are feeding the signal from here to the some system, they all will be having on the different ground. But whereas like this will be actually more preferred because they are having the common ground. So this is like single element. So the way single element is designed, this is like the microstrip excitation. So this is my microstrip excitation, and then it is actually having this. So just to reduce the space, this monopole has actually now the bent over there. So this is like the bent, and then this microstrip line, and I will say the monopole here now. This monopole is loaded with the CSRR on the back side. So this is like I'm looking this is X, Y, and this is like the Z which is coming out. And then if I will actually look this structure on the back side, so back side it will be partial ground over here, which is actually like shown here. This is my CSRR, which is complementarily split into resonator, and this is my monopole, which is printed on backside. So this element will be looking like this one. So advantage is like I'm just feeding, I'm feeding here microstrip feeding, and then this monopole is fed with the microstrip line, but this monopole is also loaded with this CSRR. So I'm getting 2 band. So it says like the case 1, you are actually having like the 1 resonance, but if you are actually loading this CSRR, you'll be actually getting the 2 band. Now this element are actually combined and form like this one, which actually show the 4 element dual band antenna. So these are like my 4 element, and these are like the dual band because like this element are loaded with the CSRR. The advantage is like if I will be looking what will be the radiation pattern because of element 1. So you'll find that because of the presence of this ground, this is this cross line, which is actually shown as the ground. Because of presence of this ground, most of the field which will be radiated will be actually tilted toward like this direction, which will be, let's say, I will say that the minus 45 degree for this one. For antenna 2, this will be like the plus 45. Antenna 3, it will be like 135 degree, and antenna 4, it will be like 180 plus 45, 225 degree on this side. So in this one, along with the polarization diversity, I'm also getting pattern diversity. So that is like the additional advantage. And second is that the bending of this monopole will actually help me to reduce area. So it says like the total footprint of this antenna, which is like the 0.26 lambda square, that will be like the this total dimension of this antenna. So yeah, so this thing I was actually talking, this element 1, if I feed antenna element 1, my main lobe, which will be actually moving toward this side, which is actually like the I'm radiating along that the 45 degrees. So if this is like the X, this is Y, this is Z, so I'm actually radiating that the 45 degree. This one is actually giving me, this is like the B, which is radiating along the 135 degree. 3, this will be actually at 225 degree. So this is actually radiating in the 225 degree, where the reference is like the X is actually going down. And this antenna, that is actually radiating along the minus 45 degree. So advantage is like we are getting pattern diversity because the each are radiating in the different direction. So these are like the pattern diversity. And if I'll compare with the 1 and 4 or the 1 and 2, they are actually orthogonal. So there will be that the good there will be like the correlation will be very small if I'll compare with the number with the 1 and 2 or 1 and 4. So here the correlation is actually calculated. It is like the 0.0005, 1 and 2. 1 and 3, this is like the 0.0023. So these are like the, so now here the correlation has actually reduced because this beam is going toward this direction, and this antenna is actually radiating in this direction. So you can actually get that very good pattern diversity. So these are like some of the response that is shown in the 2D. And these are like the TARC, total active reflection coefficient, so which are plotted. You can find out this is like a minus 10 dB and minus 10 dB. It means like the antenna is good radiator. So let us go with the one more thing. So this is the another design. So currently, like to design this MIMO antenna, this will come out to be like the 2 element, but like first let us understand that what is this antenna. So this is like one PC patch. Okay, and then I'm actually putting one dipole on this side and the dipole on this side. This is named as the dipole 1 and another one is actually named as the dipole 2. So I know that if this PC patch and this dipole 2 is not present and the antenna element which is kept along the y-axis, I will be getting this like monopole type or dipole type of radiation pattern. So in this plane, which is like the XZ plane, and I will be getting the null in along the y direction. Now because of the presence of this PEC, it will behave like reflector for dipole element 1, or this PC will behave like the reflector for dipole element 2. So this dipole element 1 and the dipole element 2 field will be modified because of presence of this PEC patch. So what will happen? So currently you are actually getting like the monopole or like the omnidirectional radiation pattern in the YZ plane. So because of the dipole 1 and the PC patch, you will not get the enough radiation along the plus X direction. It will be actually going along the minus X direction. So the field in the XZ plane, I will get the less radiation along the positive X, and I will get the more radiation along the minus X, and along the plus Z and minus Z, I will have the radiation. Similarly, if I will have the dipole element 2 I will have the good radiation along the plus x direction, but I will have the lesser radiation along the minus x direction because of the presence of this PC patch, and the radiation will be along the plus z and minus z. And that will be the case. It says like the, let's say that I am feeding this one with the one phase and this dipole 2 with the other phase, but the phase difference, let's say if it is the 0 degree, and then I'm actually changing that the this feeding phase, the what is the phase difference between two, I'm actually keep on changing. So it will not change anything on the S11, like the S11 or this S22 behavior of this antenna. So the advantage is like the resonance and the this reflection coefficient response is actually maintained. It is like the minus 10 dB, less than minus 10 dB, and the resonance is also same, that is coming close to like the 2.7 or 2.8 gigahertz. But what will happen that if I will be keep on changing this phase, which is like the feeding phase between these two elements, which is like the dipole element 1 and this dipole element 2. So it says like the if I'm feeding with the 0 degree, so you will see that I'm getting the more radiation along the plus z, more radiation along the minus z, and the radiation along the plus x and the minus x. So along the plus x, I'm getting because of the dipole 2. Along the minus x, I'm getting because of the dipole 1. So more power is along the plus z and minus z, and as compared to z direction, I have the lesser power along the plus x and the minus x, and that is shown in this figure. But now if I keep on changing the phase, how my radiation pattern is changing. And mind that by changing this phase, it is not changing your resonance, and it is not changing your magnitude of the reflection coefficient, but the radiation pattern is actually changing. So let's say like one is like this one, and if I'm changing over there, so you see that gradually it is changing 70 degree, and the moment the phase difference is like the 180 degree, I'm almost getting null along the positive z and the minus z, and I'm also getting the null along the plus z and minus z. So now if I compare this one with the feeding phase difference is that the 0 degree, and if I compare the feeding phase difference of 180 degree. So here in this case, what is that the direction of the main radiation, that is like the plus z, minus z, and the plus x, minus x. And here I am not getting the radiation along the plus x or minus x. This is plus x and minus x, or I'm not getting the significant radiation along the plus z and minus z. So the feeding, because of the feeding phase, the main radiation is like, if I go with the xz plane, I am actually having the main radiation along the plus 45 degree and the minus 45 degree. And similarly, like in this direction, I'm getting the radiation, and this direction. So if these two elements can be used as for the MIMO element, there will be like good pattern diversity. So their like correlation coefficient will be very small, because this element will be radiating along plus z, minus z, plus x, minus x, and this will be radiating that some other angle with the x-axis, which is like some conical shape of the beam is forming, which will be like along the 45 degree. So how to actually get those things? So before doing this one, so currently it is like the single element. So let us make we can have the one additional advantage, that whether we can make the dual band antenna. So this is my dipole antenna, and then actually I am loading the dipole with the CSRR. So by making that this CSRR, I'm actually getting the one additional band. So this was like the without CSRR and with CSRR. So I'm actually having this two band which are coming. One is like along with the 2.4 gigahertz. I'm also getting the one band which is along the 1.6 gigahertz. So this is like the 3D radiation pattern of this dipole antenna. So now let us see that the axis. So this is like my x-axis, this is y, and this is z-axis. So I will be getting the main radiation along the x direction, because this is now behaving like the reflector. So along the x, I'm getting the more power, and then I am having actually some power which is going in the z, and some power is going in the z. This is at the 1.7 gigahertz. This is at the 2.45 gigahertz. Now I will actually try to have that the two-pole design. So with the one, I will try to feed the one set of the dipole element, and for the another port I will try to feed the other set of the dipole element. But I'm actually trying to create that the phase delay. So here, like this is like my feeding circuit, and if I will go, so let's say like that this is only the power divider part. So if the power is fed from here, and the way the circuit is designed, both are actually so this is like the equal power division, and both port 2 and the port 3, they are getting the power in the equal phase. Now in this one, I'm actually feeding, and here that I'm actually using this additional delay line, and because of use of this additional delay line, the power is going to the port 2, and the port 3 will have the different phase. And I'm trying to create that the length such that the at the my desired frequency I should get 180 degree of the phase shift as compared to here port 2 to the port 3. So for this one, so for power divider 1, this is like the graph which is shown here as parameter for the power divider 2. So you can see that this is like the close to minus 3 dB line. So equal power is actually divided, S11 is matched, and the phase difference, that is like the power divider 1 and power divider 2. So at the design frequency, you will find it is close to like the 150 to the 180 degree of the phase difference we are actually getting in our operating range. Now this one, this is like the one part of the power divider circuit. This is another part of the power divider circuit. This is one dipole, and this is another dipole. So this is dipole 1, dipole element 1, dipole element 2. And in this network, I will say that this is like the one MIMO antenna element. So this element, both the element are fed with the same phase. So this is like the phase angle here, and the phase which is actually reaching over here, they are in the same phase. Whereas this one, they are actually having that a different phase. So here the power is coming over there, but here the power is reaching with this additional delay line. And because of this additional delay line, the phase will be different for this dipole element as compared to this one. So we have seen that this, if they are actually in the same phase, I will be having that the radiation which will be like the plus x plus z minus z. But if you have the phase difference, I will not have that the maxima along the plus z minus z or plus x minus x. So that thing is actually shown here, like it is the S11, S22 is shown, and this is like the S21, S12 is shown, which is below like the minus 20 dB. Now if I'll try to see the pattern, so if I will feed port 1, so if I'm feeding to the port 1, so main radiation is like the plus z, minus z, and the plus x minus x. And this is the 1.77. The power is actually reduced, but that is not very well captured in this figure. But you also mind that here we are not exactly getting the 180 degree phase difference at 1.77 gigahertz. But if I'll go with the 2.4 gigahertz, where actually like I'm getting the phase difference of 180 degree. So you can see that this is like the plus z minus z, I'm getting the power, and the plus x minus x I'm getting. But the other port, if I'm feeding the power at port 2, where these two elements are not fed with the same phase, I'm actually getting the main radiation along the plus 45 degree or the minus 45 degree, and similarly like the here in this direction. So it shows like that we can also design pattern diversity using the two element, and both the elements will have further the two dipole element fed with the different phase. So this is like the one of the design that is actually proposed by our group. So I don't know whether ECC has shown here. So yeah, ECC and other thing is also very good for this one, though it is not shown on the slide. This was like the one of the very basic thing. Again, like it is like 4-port thing, and each. So there are like the 4 rings. 2 rings are actually 2 slotted rings are there. No, I think this is like this is like 1 ring and the 2 ring, and then actually. So these are like not the ring. I will say these are the slot over there, circular slot, which are actually made on the ground. And then it is actually fed with the SRR, and this actually gives the quad band operation. And then if you are actually feeding with this orthogonal environment, you can get 4 elements. This one was also like the very good design which actually had done by our group. So here like so to get so what is like the we are trying to create the polarization and pattern diversity. So this is like the one of the combination. So it says like that this is a two element. So this element, first element is like the my dipole antenna, and another element is like a patch antenna. And the patch antenna, I'm actually like the cutting that the some triangle over here. I'm actually cutting that the some triangle over here, and that the advantage will be like by cutting that the extra metal part here and here, this will generate the CP, which is like the circular polarization. So if I will feed at port 1, so it will be radiating. So this is like my X, Y, Z axis. So if I'll feed the antenna at port 1, it will be generating CP radiation pattern along the positive Z direction. If I will feed the port 2, I will be getting dipole type of the radiation pattern, but because of the presence of this ground plane, most of the power will be going along the plus Y direction. So it will be like the power is going on the plus Y direction, and here the power is going along the plus Z, but it will be like the CP antenna. So it will be like the pattern diversity as well as polarization diversity. So this is like the top view, and this is like the bottom view that is shown over there. So if I will try to, so if I will actually try to look over there, so they both are operating at the 5.6 gigahertz. On this side, they are actually giving that the RSCP wave along the plus Z direction, and this one is going along the plus Y direction. So this is along the plus Y direction. So along the plus Y direction, you are getting linearly polarized wave. So these two elements can be used as the MIMO antenna element, which can be used on the application where actually you are looking at the two element system. So these are like the co and the cross polarization measurement. These are like the some ECC, TAR, and the CCL is actually shown. So you can find out that the ECC is like the below that the 0.01. The TAR is like the less than the minus 10 dB in the range, and the CCL that should be like the less than the 0.5. So within the operating band, you are actually having CCL which is less than the 0.2. Further, actually, like we have extended this paper, which is like 3 element, and which is having the pattern and the polarization diversity both. So in this one, I'm actually having 3 element. So this one is like patch antenna, and these are actually like dipole antenna. So which is actually printed on top side, and this is on the ground side. So these two combination that will make the dipole antenna. So this one along with this, that will make the dipole element, and this element along with this one, that will also make the dipole element. So now this 3 element, so if I will feed the port 1, if I'll feed the port 1, the main radiation I will be getting along the minus Y direction, and that will be like the linearly polarized wave along the minus Y direction. If I will feed the port 2, I will get main radiation along the plus Z direction, which will be CP. And if I'm feeding port 3, I will be getting linearly polarized wave, and that will be, so this will be like the plus Y direction, the radiation will be there, and I will be getting linearly polarized wave. So this one is like the 3 element polarization as well as the pattern diversity. So this is like all those parameters are calculated, like the S11 simulated and measured are actually shown, and they all are operating close to like the 5.5 to 5.6 gigahertz. And you will see that there is like good isolation between the elements. So as transmission coefficient is below minus 20 dB, and S11 is S11 and S22, they are below that the minus 10 dB. So this is also like the, so yeah, this is like the total radiation pattern. So port 1, this one is like the going along the so this radiation pattern that is going along the minus y, this one is like the plus y, and this direction is like the plus z. So these two will have the polarization. So if you see that the combination of these two elements, so they are actually representing the pattern diversity as well as the polarization diversity. So these are actually like my response. This is like the gain. What is like the actual issue? You will find like the actual issue that is like the below 3 dB in the design, and this is like some simulation. There is small shift in the frequency. So this is like the TARC. So you can find out like the TARC is like the below minus 10 dB in the all those range, and this is like that my channel capacity loss. So that is below. So it should be like less than 0.5, but it is like at the operating frequency they are actually below 0.2. So this is like the one of the design for MIMO antenna. The advantage is like that this is like 3 element, and all those elements are that very closely packed over there, and you are having the patternal polarization diversity both in this type of structure. I have some 4 or 5 slides on the massive MIMO. So people are actually talking about this massive MIMO. So it means like you are not having like the 2 element 4 element. On the base station, you are talking about like the 64 element or the 256 element system, and so that I can actually have beam forming either in the vertical plane or in the horizontal plane. So it means that this antenna has to be packed with the more number of element. So some of the analysis that was actually done by this. So this one is like the slide from the key side. So they have shown. So this is like 4 user system. So these are like the 4 user which are actually present, and this base station which will having like the close to like 200 element which are actually kept over there. And then if you will optimize the response, so you can see that if I want to create the beam only on the user 1, so this is like the only on the user 1, user 2, 3 and the 4, they are actually lying in the null direction. Similarly, let's say that I want to feed the power to the user 2. So this 1, 3 and 4, they are actually in the null direction. Similarly, I can also control like the phase pattern over there. So user 2, 1 and 4 are the null, only that the beam can be formed along with the user 3. And similarly, like the 1, 2, 3 are the null position, but the only user 4 are actually receiving the beam. But that will be only possible if you are having actually like the 200 element. So they showed like this one 0 dB of the power they are actually transmitting. So this is like the 200 element. I think that I missed that how many element they are actually using for this slide. So they have actually the 200 element they are actually using, and the difference among the element are like the lambda by 2, and the relative power difference is minus 9.5 dB. So if you are having more number of element, you can actually see that you can have very sharp beam along the one of the user, but other 3 user, they are actually lying on the null position. Similarly for the other cases. But like how to place that those 200 element or those ones, so still like the people are doing those type of analysis. So if we are talking about this base station antenna, so they are having both the polarization, they have the vertical polarization as well as they are actually having the horizontal polarization. So this is like shown the one of the element. So these are like my patch antenna, and this so this is like on the top layer. Then we are actually having some dielectric over there. Then these are like some metal coupling. Then this is like my ground. Within that the ground we have cut that the slot. Then we are having the another layer which are dielectric, and then I am having this feeding network. So from this picture you can see this is port 1 and this is port 2. So port 1, if I'm feeding, so the power is going like this one. So this is actually power is going on this feeding network and then coupled with this slot, and these slots are there. And then this slot are actually exciting so So one of the patch system, I'm actually exciting that with the horizontal configuration, one of the patch system we are actually exciting with the vertical configuration. So this like the port one, if I will feed, I will excite that the two of this element, which will be actually giving me the horizontal polarization, and the two that will be giving me the horizontal. So two is the horizontal and two will be actually giving the vertical polarization. So then they have actually done this analysis. So after that, they have actually arranged that this array. So this is like the 16 element, and this one feeding network is actually exciting that the two pair. So ultimately, it is like the 4 port which will be exciting the your vertical configuration, and the set which will be actually exciting the horizontal configuration. So it is like the 4 element on this side and the 4 element on this side. So it is like the 8 port network is actually given. And then you can actually enhance that this stacking of this patch. I mean, like you can actually go on the vertical direction, and you can further increase the number of element. And the advantage is like I'm actually having this ports which are actually coming out from here. I can feed this each patch, like this one combination is actually feeding 2 patch. But in that case, like consider that this is the one element. So I am actually can feed this with the different phase, and by controlling that this with the different phase, I can actually control like in which direction I want to form that beam. So this is like the combination which is actually shown over here. This is like the 3 layer. So 1, 2, and 3, and then it is actually kept in the hexagonal. So I've shown that the result for this one, which is like the 16 element, ultimately it is has the 8 port over there. So it is 8 port. This is another 8 port, and this is another 8 port. So this is like the 24 port on this one, which is actually shown from the C1, C2, C3, C4. So these are like the number of elements C1, C2, C3, C4. And then actually I'm having this hexagonal arrangement. So total number of actually element that will be like the 24. And then actually I'm arranging in the vertical fashion. So this is like B1 to the B24 and A1 to A24. So what they have done, like if you'll be looking, like it is like the 74 element that is actually there, but each element is also consists of four patches. So it is like 72 multiplied by the 4. So 72 multiplied by 4, so it is like the 248. 288 element. So 4 to the 8, yeah 72 288 element. So this is actually ultimately the 288 element, but it is like the 18 sub array. So it is like the 6 sub array. So if I want, I can actually increase that the stacking in the vertical direction, and I can create the more number of sub array as per the my requirement. The advantage is like I can. So if it is like the one hexagonal, I can actually, so each hexagonal I can have the one beam which is actually forming, and this beam is actually formed because of this 4 elements. So this is like the one beam forming is over here. Now I can actually stack that the second layer. So I can actually have that the another set of the beam forming, and then the third set which is another set of the beam forming. So you can see that by 18 sub array, I can actually get that the 18 beams, and all these beams are actually simultaneously radiating. So this is like the one way that the people are looking to design that the massive MIMO over there. And mind that like if currently like these are like I'm considering that this each element are the sub array, but you can also use the combination of this one on the vertical direction and then form the beam in the other direction. So this one is like another geometry where actually people have shown for the massive MIMO for the base station. So this is like the 120-degree sector. This is one, this is second, and this is third. And within that the 120-degree sector, you can have that this patch environment. So here, if you'll see that this is one element which is combination of the 4 patch, and I have the 6 layer on this side, 1, 2, 3, 4, 5, 6, and then I'm having like the 4 on this side. So it is like the 24 element there are 24 and each element is consist of that the 4 patch. So 24 cross 4, it is like 96 element, which are actually 96 patch element are there. But let's say like we are considering that this one as the one subarray, and I am actually having that 24 subarray. Now the combination of this one, either on the vertical side or a combination on the horizontal side, I can use to focus the beam towards that the particular direction. Okay, like I can actually let's say that if I'm actually taking that this set which is actually on the vertical direction 1 2 3 4 5 6, then I can actually scan that the beam in the vertical plane. If I will be using that this array like that the 1 2 3 and 4, or I can actually further increase, so that will be the scanning in the horizontal direction. Or I can actually take the combination of these tiles with the other tiles, and I can have the scanning in the vertical and horizontal direction simultaneously. So these are like the proposal which actually people are proposing for the massive MIMO at the base station. So currently we are only talking about the front panel, but the back side you have to have actually those feeding network, because if you are having, let's say, the 256 element or 288 element, you need that the very large network of this Butler matrix or the phase shifter network, so that you can control the phase of the individual element. Just to show the reason to show here is like by using this set, I can actually scan that the beam in the vertical direction. By actually using this combination, I can use that the horizontal direction, or I can use like this one is one horizontal direction, this is like the other horizontal direction, or I can use the combination of this one, which will be actually forming the one beam, and the set which is actually forming the beam in other direction. So depending upon the requirement and depending upon the number of user, we can actually focus the beam toward the particular direction. So this is like the proposal for the 5G base station, which is actually the massive MIMO system. This is like some fabricated. So this is from the Sharavi group. This is a very famous group over here. So they have actually demonstrated this one. They have also done the experiment. So this is like 24 sub-array, and each sub-array consists of the 4 elements. So they have actually shown that the dose response. So these are like their measured radiation pattern for each sub-array, and they have shown like how that you can actually tilt that beam. Thank you.
So if anybody has any question or queries, please ask. You can ask.
See, the last array which you have shown requires a lot of dynamic planning based on the traffic which you have. So whether you want to scan the beam horizontally, vertically, or whether you need to use only 2 stacks or 4 stacks or more number of stacks, will again depend on the density and this. So it requires a very large software or logic to make sure. And because in 5G, also the latency period is very, very less compared to earlier ones. So I'm sure this array should be able to handle that, I suppose.
I also hope so.
Any experiment has been done or any results are available?
No, I think at the commercial level, very few results are actually there, and still like this companies are not sharing those results. So this is like whatever the result or whatever the structure, this is like by the research group what they are demonstrating.
No, in a particular locality, if there are it. So there is
yes,
a big
I agree.
office area.
Yes,
the number of users will be very large. So in which case they can easily focus beam to that direction with a high power. Whereas in a place where you don't have very dense population, then you can put a much lower power and a wider beam.
Yes, I agree. I agree. I agree with you. One thing is what
I'm saying is this logic which they have, you have to make sure that you have a complete processor which would do the job. So that is the main brain in this whole thing.
Yes, and another thing is like this base station may not be directly actually communicating with the individual user. This main base station will be actually contacting to the sub base station, and then the sub base station will be actually talking directly with the user.
That's good. That way it will be
so
much,
that's
slightly
that,
easing out the system.
So that will reduce the complexity.
Yeah, very good. This is a very good design, and we are really looking for such things to come up in India.
Yes, yeah.
It's a great, it's a very great, very good work.
Yeah.
Thank you.
Thank you.
So any more question? Sir, one thing I have in mind, like in the millimeter wave, whenever like people are now working toward means after 26 gigahertz or 30 or 40. So like massive MIMO concept, I think it will be very difficult to implement.
Actually, one thing is like this millimeter wave, the moment you are actually going, first thing is that you should have this your channel model ready. So enough study has not been done on the channel model at 28 gigahertz. Second thing is, if you are going at 28, the moment you are going for the higher frequency, your range, because that the attenuation will be faster the moment you are going on. So at the 5G, and you are talking about this millimeter wave, whether that you will get the enough coverage. Let's say like for this base station, we are looking the coverage in the range of 2 kilometer to the 5 or 6 kilometer. So whether we will be getting those range at the 28 gigahertz or 30 gigahertz, that is the challenge. And third thing is like if you are going to the massive MIMO, the another disadvantage is like the element size will be that the very small, and then you are actually trying to pack so many elements. So let's say that there's so because we are also actually looking for the massive MIMO for this millimeter wave. The thing is like if your antenna element is like the very close by, so then you have to excite those antenna elements. So you have to have those excitation such that they can be feeded at the desired phase. So let's say you're thinking of your at 30 gigahertz. If you talk about that the element size, so that is like at 10 gigahertz it is the 3 centimeter. At 30 gigahertz it is 1 centimeter. So your antenna element size itself is like that the 0.5 or the 5 mm, and then you are connecting with the 2.92 mm connector. So whether you are having that enough density to excite those elements. So those are like the various challenges at the millimeter wave for this massive MIMO. Unless you will go everything on chip.
Okay.
Yep.
So any more question from any audience? So, sir, one more thing, like, is there any possibility of 3D printing antenna design that for this massive MIMO, or I think 3D printing, I think it will be difficult for millimeter. I'm not sure, but for like massive MIMO, like till now, I've not gone for any literature survey about that. So I think is there any possibility of going in that area?
So whenever you say that the 3D printing, you are looking for the multi-layer of the antenna, or only for the printing of the antenna you are going for 3D?
The printing.
Printing, you can go with the 3D. What is the there is no challenge. Like if you have the printer which can have the printing with the dielectric and the metal printer, which can go, you can do. Advantage to go to 3D is like if you are looking for the multi-layer configuration, then you will have the advantage. Where that the one layer you want to actually design that the one set of the antenna, and the set you are actually. So let's say like sometimes people go for the shared aperture. Okay, so then the people actually on the one layer they design the, let's say for the expand antenna, and the layer they design the KU band antenna. So there you will get the advantage unless you are having the different band of the antenna. Okay, otherwise like if you are having this normal photolithography, and you are actually having the same layer, on the same layer you can actually print the antenna, that will be like the cost effective. Okay. So multi-layer, if you are going, yeah, definitely that the 3D printing will help.
Because sir, like if whenever we talk about MIMO, we talk about polarization diversity and like pattern diversity. So whenever if you are orienting like let's say monopole or only in different orientation in 3 dimension, so we will be having more flexibility in reducing the ECC.
No, but the thing is like the currently you are putting the orthogonal polarization, but if you are actually going into the 3 dimensional, it means like the antenna element or the thickness along the z direction should be the dimension of the antenna.
Yes, yes, sir.
So whether you can actually tolerate that much space or that much volume.
Okay, okay.
Okay, so if that much volume you can sacrifice, then you can actually think of going the placement along the z direction as well. Maybe if you are going in the high frequency, that will be good to get because if the element size is very small, then you can actually have the advantage going in the 3rd dimension.
In like sir, in millimeter wave, there is like dielectric resonator antenna are becoming more popular for in MIMO antenna design. So I think maybe that can be one of the reason. Like means the size can be one of the reason. Okay, I think like there is no more question from the audience side. So, sir, it was a very nice session, and we got to know a lot from the starting from the basics to the like current state of art. So, I I thank you again for this session, and I will request all the audience for kindly attend the another session of this workshop. So, we are going to have the next session of the workshop on Friday in between 2 p.m. Between 2 p.m. to 5 p.m. So, first session will be on between two start from 2:30 p.m. on Friday. So that will be again on the one of the other area of microwave millimeter wave technology, which is going to be covering the frequency selective structures application. Okay, sir. Thank
Thank
you,
you.
sir. I'm
Thank
just seeing like any chat window if there is any question or not. So I think there is
There is
no more
no
question is
question.
there.
Okay.
Okay, sir.
Okay. Thank you,
Okay, sir.
Vishwanta.
Thank
Thank
you.
you. Thank you.